As we know, P block elements carry 10 mark weightage in the exams that are going to be held in the end of this year, that is 2021. So P block elements are basically the ones which are present on the right side of the periodic table. We know that. And in this chapter, you'd be learning about group 15, 16, 17, and 18. And if you notice in the syllabus, you have certain topics which are common for all of them, like the general introduction, the electronic configuration, oxidation state, occurrence, as well as trends in physical and chemical properties. So these 5 topics, it's better to learn them as a simultaneous thing instead of learning them individually. So we will be doing that simultaneously or parallelly for all the 4 groups. And there are also you'll also have to learn about various compounds of uh, each of these elements in the group. So we'll be learning about them as well. One important thing for 2021, 2022, we do not have the phosphorus compounds included. So it has been removed from the syllabus. So let's start with the general introduction. So each of these groups we'll be learning about we're going to be talking about the elements of each of these groups, the occurrence, and because the occurrence is basically a theoretical topic, I would suggest you to go through all of the occurrence of all of these elements in this table, and it includes everything, almost everything in the textbook, and the electronic configuration. So group 15 is the nitrogen family. It consists of the elements nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. The electronic configuration is Ns2Np3. Notice we have a half full orbital in case of Np3 and a completely full orbital in case of Ns2. And because of this, the nitrogen family is actually quite stable because of the half full p orbital, as well as a completely full s orbital. Next, oxygen family. It consists of oxygen, sulfur, selenium, tellurium, polonium, and livermorium. Now, oxygen, sulfur, selenium, and tellurium are also referred to as chalcogens. The reason is they are called, basically the word chalcogen means they're ore forming elements. Okay, so basically almost all the metals that we obtain from the Earth's crust are in the form of their oxides and sulfides. And because of that, various metallurgical processes involve the removal of the metal or the extraction of the metal from its oxide and sulfide. And so elements of group 16, especially the first 4, are called as chalcogens. The next, they have the electronic configuration of Ns2Np4, and they have 6 electrons in their outermost shell. The next family is the halogens. They consist of fluorine, chlorine, bromine, iodine, astatine, and tennessine. And they are basically form salts. Okay, so they are on the right extreme of the periodic table, that is before the noble gases. And they usually react with the elements in the first and the second group to lead to the formation of salts. And they show one unique thing about the halogens is the fact that they show good gradation in terms of various properties, and astatine and tennessine are radioactive elements, and their electronic configuration is Ns2Np5. The last family, that's on the right extreme of the periodic table, are noble gases, and helium, neon, argon, krypton, xenon, radon, and oganesson. That is one of the most recent additions to the periodic table, oganesson. And they're very unreactive, and they form very few compounds. And you'll be learning only about certain compounds which have been formed, and they've been with extremely electronegative atoms. So they show very less amount of reactivity. And noble gases have the electronic configuration of Ns2Np6. So here, remember all the occurrence. You can just go through it and basically learn it. So let's start with the discussion about physical properties. So here in this table, you have the group 15, 16, 17, and 18. That's the group name number rather. And here you have all the physical properties. So we're going to be talking about atomic radius to ionization enthalpy to even allotropy. So let's start with the atomic and ionic radii. So both of these generally across the period, there will be a decrease in the atomic radius. And as we go down the group, there is an increase in the atomic radius. That is what we learned in grade 11. So group 15, that is the nitrogen family, both the covalent and the ionic radii will increase on going down the group. But one thing you need to remember, nitrogen to phosphorus, there will be a good amount of increase in the atomic radius, but there is only going to be a small amount of increase from arsenic to bismuth. And this is because of the weak shielding effect of the d orbitals. So as we know, the shielding effect is highest for the s orbital, and it's the least for the f orbital. And because of that, the nuclear charge is able to pull in the electrons towards itself, and so it's able to have a good hold on it. And because of that, the covalent radius for arsenic to bismuth is not increasing drastically, but only to a certain extent. Next, group 16, you have the atomic and ionic radii increasing down the group, obviously because of the increase in the number of shells. And the size of the oxygen atom is going to be really small. Next is the halogens. So it has a strong nuclear charge, and generally in each period, the halogen atom is going to be the smallest in its period. Okay, and fluorine atomic radius is very small because it's similar to the elements in the second period of the periodic table. So nitrogen, oxygen, fluorine, all of these elements have a very small atomic radius. And as it goes for the other groups in the periodic table, the atomic radius is going to increase on going down the group. Same thing goes for group 18 as well. So atomic radius increases on going down the group with increase in the atomic number. So notice, by learning it as a comparative idea, you do not have to individually study, okay, fine, group 15, there's an increase, group 16, there's an increase. You don't have to do that. You can just say that in all these cases, you have an increase in atomic radius on going down the group. And in case of each group, there is one specific, property of its own. Next is the ionization enthalpy. So as we know, the ionization enthalpy is basically the ability for us to remove an electron from that particular isolated gaseous atom. So in group 15, there is an increase in the atomic radius as we go down the group. So the ionization enthalpy will decrease. But one thing you need to remember, group 15, the ionization enthalpy of group 15 will be higher than group 14 or group 16. And this is because of its half-filled p orbital and completely filled s orbital. And one more thing, the first ionization enthalpy will be less compared to the second, which will be obviously greater, than third will be the greatest. Next is group 16. Of course, due to the same thing applies to this as well. So the ionization enthalpy decreases on going down the group. Now, the ionization enthalpy is lesser than group 15 because group 16 does not have a half-filled p orbital. Next, group 17, they have a higher ionization enthalpy. Now, halogens, they require only one more electron to gain the electronic configuration of the noble gas. So it is very difficult to remove an electron from halogens. So the ionization enthalpy will obviously, again, in this case also decrease as we go down the group. But one thing here, the ionization enthalpy for halogens is the highest. Now, in case of group 18, that is our noble gases, they have a very stable electronic configuration. So they have very less very less tendency to lose the electron. So they will have a very high ionization enthalpy. But the ionization enthalpy, again, in this case, will decrease on going down the group due to increase in atomic size. So this one statement, decrease of ionization enthalpy due to increase in the atomic radius, is common for all of these four groups. Next is electron gain enthalpy. Now, electron gain enthalpy, I'm sure you would have learned it last year. It basically gives us the measure to show how easy it is to add an electron and form an anion. So negative electron gain enthalpy means energy is released when an electron gets added, and positive electron gain enthalpy means energy is required for us to add the electrons. So negative gain enthalpy means that it's easy for us to add the electrons, basically. So let's start with group 16. So oxygen has a less negative electron gain enthalpy than sulfur. So the reason that this is the case is because oxygen has a very small size and it requires a little amount of energy more than sulfur for addition of an electron. If you remember, you would have learned about all of this in grade 11. So from sulfur onwards, the value obviously becomes less negative up to polonium because it requires a little more energy to add the electrons compared to sulfur. Next are halogens. They have the maximum negative electron gain enthalpy. It does not even require a lot of energy to add the electron because they themselves have a tendency to accept electron. This is because they want to get to the noble gas configuration. Now, the electron gain enthalpy was obviously going to become less negative as we go down the group. And it's again similar to this case. Fluorine is less negative than that of chlorine, and this because of the small size. And also one more thing, we have a lot of interelectronic repulsions in the 2p orbital, and because of that, the incoming electron does not experience a lot of attraction. And the same reason why we have oxygen having a less negative electron gain enthalpy than sulfur. So this particular reason is applicable to this, but this oxygen as well. Next, obviously, noble gases, they have no tendency of accepting electrons. So since they don't have that, they have a huge positive value of electron gain enthalpy, which means energy has to be supplied for an electron to be added to the noble gases. Next is electronegativity. Electronegativity is basically to the extent to which an electron can be pulled by an atom, right? So this is especially when we have a bond in between two atoms. So electronegativity in case of group 15, it decreases down the group because there is an increase in the atomic radius. Now between the heavier elements, the difference of electronegativity is not very, very different because the atomic radius is not varying to a great extent. Next, in case of our oxygen family, after fluorine, oxygen has the most electronegative. Oxygen is the second most electronegative element in the periodic table. And electronegativity decreases as we go down the group with the increase in the atomic number. Also, this means that the metallic character increases from oxygen to polonium. So metallic character basically implies that an atom has the tendency to lose an electron. So metallic character increases as we go down the group. Obviously is because of the fact that you have an increase in the atomic radius. Now, the group 17, they have high electronegativity in each period, and fluorine is the most electronegative element in the periodic table. And this is a blank because noble gases are not electronegative because they're pretty satisfied. Atomicity. So atomicity is basically the number of atoms in one molecule of an element. So in case of nitrogen family, you have all the elements being polyatomic in nature, whereas dinitrogen is the diatomic gas. And when we talk about our noble gases, they are monoatomic, means they exist alone. Next is the state, that is solid, liquid, or gases. Dinitrogen is a gas. Remaining others, they are going to be solids. Whereas fluorine, in case of halogens, fluorine and chlorine are gases. Bromine is a liquid. Bromine is a liquid, whereas an iodine is a solid. So they have various states. So you have a gas, liquid, as well as a solid. Noble gases are all gases. Metallic character. So metals have a tendency, as I told you, they have a tendency to lose electrons. Non-metals have a tendency to gain electrons. Generally, metalloids are between and they show certain properties of both metals and non-metals. So in case of nitrogen family, the metallic character is going to increase as we go down the group. And this is obviously because as we go down the group, the atomic radius increases, so the ionization enthalpy is increasing. So nitrogen and phosphorus are non-metals, arsenic and antimony are metalloids, and bismuth is a metal. In oxygen family, you have the oxygen and sulfur as non-metals. Selenium and tellurium are metalloids, whereas polonium is a metal. And one more thing, polonium is a radioactive element and it is short-lived. Next is the boiling and melting points. Boiling point is basically the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. Melting point is the temperature at which the solid changes to a liquid. So as we go down the group, there is going to be an increase in melting point, and it only increases up to arsenic, and then again it decreases as from up to bismuth. From arsenic to bismuth, there's a decrease in the melting point. Next, the melting point and boiling point increase with increase in the atomic number. And there is a large difference in melting points because between oxygen and sulfur. And this is because oxygen exists as a diatomic molecule, that is O2, whereas sulfur is existing as a polyatomic molecule. And because of this variation in the number of atoms in their atomic or rather the molecule of each element, because there's a huge difference, there is a large difference in between these two elements, melting as well as boiling points. Now, in case of halogens, they increase with increase in atomic number, both of them. Whereas in case of noble gases, they have very low melting and boiling point. And this is because, very important, they have weak dispersion forces in between them. Because they have a weak dispersion force in between them, there's not going to be a lot of attractive forces between the atoms of noble gases to hold them together. And because of that, they have very low melting and boiling points. One more thing, helium has the lowest boiling point of any known substance. So, yeah. Next is allotropy property. So this is, allotropy. If you think about allotropy, the first thing you think about is graphite, carbon's allotropes, graphite, diamond. So they have the same atom, but they have variation in physical properties, but they'll have similarity in terms of chemical properties. So in case of nitrogen family, all the elements except nitrogen show allotropy. And in case of the oxygen family, you have oxygen family, all these elements show allotropy. Now here we have certain points which couldn't be included in any of these, so I just put them in a separate part of the table. So first of all, color. Halogens are actually colored, and this is because they tend to absorb radiation in the visible region. Okay, and when they do absorb the radiation, the electrons, they jump up to a higher level. And because they are doing that, because there is an excitation of electrons, you have a variation in terms of color. So fluorine is a yellow colored substance. Chlorine, on the other hand, is greenish yellow. Bromine is red. Iodine is violet. So because of that, you have a variation in color because of the excitation of electrons. So you have the excitation of electrons, which is why they are colored. Now, solubility. Fluorine and chlorine react with water, but bromine and iodine are not that soluble in water. But generally, they are soluble in various organic solvents like chloroform, carbon tetrachloride, carbon disulfide, hydrocarbons. Then they give us a colored solution. Enthalpy of dissociation. Enthalpy of dissociation basically means that the ability for us to break a bond. So for fluorine, it will be lesser than that of chlorine. And this is because in fluorine, they're small sized, right? Because they are small sized atoms, what happens is the electrons basically repel each other. So they want to fight each other and they easily get separated. So the enthalpy of dissociation is less for for fluorine than that of fluorine. So as it's written over here, the reason for this is the electron-electron repulsion among the lone pair of electrons which are closer together. So if they're closer together, they obviously want to be farther apart because repulsions. So after chlorine, the enthalpy of dissociation increases in the order chlorine is more than bromine than the iodine molecule. Next, in noble gases, these are the unique points. First of all, they are colorless, odorless, as well as tasteless. They are sparingly soluble in water. Helium has a very unusual property of diffusing through most and commonly used laboratory materials like rubber, glass, or even plastic. So it is a very unique element. So with that, we're done with the various physical properties that we have in this chapter for group 15, 16, 17, and 18. So let's start with the chemical properties. The first one is oxidation state. So the oxidation state shown by group 15 elements are -3, +3, and +5. The reason you have a -3 oxidation state is because when they gain 3 electrons, they have the configuration of noble gases, that is NS2, NP6. But this requires a lot of energy, and the tendency to form this -3 oxidation state actually decreases as we go down the group. And this is because as we go down the group, there is going to be an increase in the atomic radius, and the tendency to lose electrons will increase. That is, the metallic character is actually increasing as we go down the group. Bismuth does not even form compounds with the -3 oxidation state. Next is +5 oxidation state. So +5 as in these 3 electrons, and these 2 electrons are going to get lost. And the stability, similar to -3, actually decreases as we go down the group. And the well-characterized compound of BiF3 is actually formed with the +5 oxidation state. So a high amount of energy is actually required for the formation of the +5 ions. And these compounds are actually covalent in nature. Next is the +3 oxidation state, which means these 3 electrons are going to get removed. So you have an NS2 as the outermost electronic configuration. And the stability of this N+3 oxidation state actually increases as we go down the group. And this is because of something called as inert pair effect. Now, inert pair effect means that the electrons of the outermost s orbital is going to remain unshared. And because of that, you just have an NS2, right? So this is going to provide some amount of stability. And because of that, the +3 oxidation stability is increasing as we go down the group. So in case of arsenic, antimony, and bismuth, it is going to become increasingly stable with respect to disproportionation. Next, we are going to talk about nitrogen. Nitrogen actually shows 4 different types of oxidation states. That's +5, 1, 2, 3, and 4. But +5 oxidation state, it does not even form compounds with the +5 oxidation state. The reason for this is because there is no d orbitals in nitrogen. And because of that, it cannot form compounds with a +5 oxidation state. Now, in case of +1 to +4, it tends to disproportionate, which means that when you have a compound, it undergoes, if I think you would have learned about it in grade 11. So this particular compound undergoes parallel oxidation as well as reduction, or rather simultaneous oxidation and reduction. So here, HNO2, the oxidation state of nitrogen is +3. In HNO3, the oxidation state is +5, and in case of NO, it is +2. So +3 is changing to +2, whereas again +3 is going to change to +5. So here there is an increase in the oxidation state, and here there is a decrease, showing that it has undergone parallel reduction as well as oxidation. Phosphorus, on the other hand, shows +4 and +1 states in some oxoacids. So oxoacids are basically acidic compounds which are formed when a particular element is reacting with oxygen. And oxidation states of this particular, all the intermediates, they form they change to +5 and -3. Covalency 4. Nitrogen is actually restricted to have a maximum covalency of 4. And the reason for this is because it has 4s and 2s and I'm so sorry, 1s and 3p orbitals are available, which means it has only 4 orbitals which are available for bonding. And after that, I mean, it does not have a d orbital for bonding to take place. And because of that, when we talk about covalency, nitrogen has a maximum covalency of 4. And it basically, whereas in case of the others, they can use the outermost shell with the d orbital to have multiple bonds, and because of that, they can expand their covalency. Next, we're talking about group 16. Oxygen family. So NS2 and NP4 is their electronic configuration. So here, outermost electronic configuration. Here, oxygen has -2, -1, 1, and 2. Sulfur, -2, 2, 4, and 6. Selenium has -2, 2, 4, and 6 as the oxidation states. Tellurium, -2, 2, 4, 6. And polonium has 2 and 4. Now, the reason you have -2 is because they just need 2 more electrons to gain the noble gas configuration. So the stability of the -2 state decreases as we go down the group. Now, this is oxygen is very electronegative in nature. So it tends to basically, it can show the -2 oxidation state. In case of OF2, its oxidation state is +2. And the reason that is even happening is because fluorine is more electronegative than oxygen. Polonium hardly shows -2 oxidation state. Now, the other elements, as it's obvious over here, show +2, 4, and 6 oxidation states, but the +4 and +6 are actually more common. Now, let's look at +4 oxidation state. Sulfur, selenium, and tellurium, they form compounds with oxygen. And because of, this is obviously going to again be because of the high electronegativity of oxygen. Now, when we go down the group, the stability of the +4 oxidation state is going to increase. And this is similar to the case of our +3 oxidation state because of inert pair effect. So when 4 electrons are lost, then you only have an NS2, and NS2 will show the inert pair, and this will lead to the inert pair effect. +6 oxidation state, on the other hand, the stability of this decreases as we go down the group. Remember, notice there are some similarities. Here it was +5 and +3, and +5 decreased as we go down the group. And this is the same case over here. As +3 increased as we go down the group. And similarly, +4 increases as we go down the group. The reason is actually same. Now, sulfur, selenium, and tellurium, they show +6 oxidation with fluorine. Here it was with oxygen. Here it is with fluorine. Bonding in +4 and +6, they are basically covalent in nature. Now, let's look at halogens, that is group 17. Now, all of them will obviously show the -1 oxidation state because they just require 1 more electron for the noble gas configuration. Chlorine, bromine, and iodine show +1, 3, +5, and +7 oxidation states too. And the reason is this. So when there is, so this one is for the elements which are not fluorine. So this is the ground state configuration, and that's why they have a +1 and a -1 oxidation state. But when they have the first excited state, you have 1 electron again being unpaired, and you have an Nd orbital. And so the electron gets pushed, and you have 3 unpaired electrons. So it shows the +3 oxidation state. The second excited state has 5 electrons, which are unpaired, and that shows a +5 oxidation state. And in case of a third excited state, you have 7 electrons, which are unpaired. And actually this had to be removed. So you do not have one here, this downward arrow, this electron does not exist here, and this actually moves here. So you have 7 electrons which are unpaired. That's why you have a difference in terms of 5 and 7. Here this basically gets unpaired, right? So when halogens, they combine with electronegative atoms like fluorine and oxygen, and they form interhalogens, oxides, and oxo acids. So interhalogens is when you have two different halogen atoms reacting with each other. Now, oxidation states of +4 and +6 are observed for oxides and oxo acids of chlorine and bromine. So for oxo acids and oxides of chlorine and bromine, you have an oxidation state of +4 as well as +6. Now, obviously, fluorine atom, the reason you only have -1 for fluorine is because it does not have d orbital. So all of this wouldn't even take place. And halogens are obviously very reactive. So they react with almost all the elements. So they react with metals, they react with non-metals, and they form halides. And obviously, as we go down the group, the reactivity of halogens also decreases. Now, an oxidizing agent is one which has the ability to lose to help in oxidation, which means it itself should undergo reduction. And reduction basically means gain of electrons, and halogens really want those electrons. And so all the halogens are actually very good oxidizing agents. So fluorine is actually the strongest oxidizing halogen, and it's capable of oxidizing other halide ions as well. So you have fluorine and it reacting with 2x minus, and X could be any halogen, that is chlorine, bromine, or iodine. Notice there's a pattern. The ones below them, they are able to oxidize the elements which are below them. So fluorine can oxidize chlorine, bromine, and iodine. Chlorine can oxidize bromine and iodine. Bromine can oxidize just iodine. And the reason for decreasing is because of their electrode potential, which is decreasing. If you can, if you notice that the table given, you can see that the electrode potential is varying as we go down the group. Now, actually, fluorine is able to oxidize water to oxygen. So you have fluorine is able to oxidize water to give us a separate oxygen molecule. Next, chlorine and bromine, they react with water to give HX and HOX. HX is hydrohalic and hydrohalic acid, whereas HOX is hypohalous acid. So chlorine and bromine are able to react with water to give us hydrohalic and hypohalous acids. Iodine, on the other hand, is, the reaction is actually non-spontaneous, but I minus can be oxidized by oxygen in acidic medium. And this is basically the other way around of what is observed in case of fluorine. So fluorine is oxidizing H2, oxidizes water to give us oxygen, whereas iodine is itself getting oxidized for us to get water. It's just the opposite. The next is reactivity towards hydrogen. So all of these three groups, all of them react with hydrogen. Now, when they react with hydrogen, they form something called as hydrides. So in case of group 15 elements, you have EH3 as the hydride forming. Group 16 elements form H2E, whereas group 17 elements form HX. So E can be nitrogen, phosphorus, arsenic, antimony, and bismuth. And there's a table in the textbook which shows the various properties of these hydrides. So before we start talking about this, there's something called as bond dissociation enthalpy. Bond dissociation enthalpy is basically the amount of energy which is required to break one mole of the bond. So when you have a long bond, when the bond between two atoms is, when the two atoms are big, the bond is going to be longer than when it is smaller. So the bond dissociation enthalpy for the longer bond is actually lesser than that of a shorter bond. Just remember that. So let's start. Stability of hydrides is obviously going to decrease as we go down the group. This is because the bond dissociation enthalpy decreases. Now, this also implies that the reduction power of these hydrides is going to increase as we go down the group. Ammonia is just mildly reducing, whereas BiH3, bismuth hydride, is actually a very strong reducing agent amongst the lot. So the basicity is going to be ammonia is the most basic, and bismuth hydride is the least basic. Now, one important property ammonia shows is hydrogen bonding. So it can show hydrogen bonding in solid and liquid state. The reason that this is observed is because nitrogen has a small size and it's highly electronegative compared to the other elements in the group, and because of that, it's able to form strong hydrogen bonds. And so NH3 actually has a higher melting point as well as boiling point than that of PH3, phosphorus hydride. So here we talk about stability of hydride decreasing as we go down the group. This is because of decrease in bond dissociation enthalpy, and their reducing power, which increases as we go down the group. Next, in case of chalcogens, they form H2E, basically H2O, remember. So the acidic character increases as we go down the group. Now, this is again related to its bond enthalpy of dissociation is increasing as we go because is decreasing as we go down the group. So it is easier for these elements to, compounds to donate their H plus to form acidic solutions. So the acidic character increases on going down the group. To remember this, you can just think that water is not at all, it's neutral, right? So the acidity increases as we go down the group. Now, thermal stability. Thermal stability, now if you notice, there is a decrease in bond enthalpy of dissociation, which means it is easy to break these bonds, which obviously will imply that their enthalpy, thermal stability, is going to decrease as we go down the group. Reducing property, on the other hand, is shown by all the elements except all the hydrides except for water. And it increases from as we go down the group. So similar to the reducing power of our previous group, the property is going to decrease. Here also, it's obvious that as we go down the group, the reducing character increases. Here also, the reducing character increases as we go down the group. Last is halogens. So halogens, they react with hydrogen to give hydrogen halides, that is HX. So when HX gets dissolved in water, it forms hydrohalic acid. And the acidic strength is the highest for HI and the least for HF. And as we go down the group, the stability is going to decrease. So HF is the most stable, whereas HI is the least stable. And this is obviously, again, due to the decrease in the bond dissociation enthalpy. So for hydrides, remember these words: bond dissociation enthalpy, and based on that, relate your answers. Next is reactivity towards oxygen. So they form something called as oxides. So oxides of these elements, in case of nitrogen family, you have E2O3 and E2O5 forming. So oxides which have a higher oxidation state of the element, they're basically going to be more acidic than that of lower oxidation state. And as we go down the group, the acidic character decreases. The acidic character decreases. Basically, when this oxide can, when it's dissolved in water, it leads to the formation of acid or base. And based on that, we decide about its acidic character or basic character. So acidic characters of the oxide decreases as we go down the group. So the oxides of E2O3, nitrogen and phosphorus, they are purely acidic in nature. In case of arsenic and antimony, they're amphoteric, and bismuth is predominantly basic. So acidic character decreases as we go down the group. Next, in case of the oxygen family, they form EO2 and EO3 oxides. So E can be sulfur, selenium, tellurium, and polonium. Notice we're not included oxygen in this case, because oxygen forms only O3, that is ozone. So you have O3 and SO2, which are basically oxides, and they are gases, whereas selenium oxide is a solid. So the reducing property decreases as we go down the group. So sulfur dioxide is reducing, tellurium oxide is an oxidizing agent. And both types of oxides, in this case, EO2 and EO3, are acidic in nature. We'll be discussing about the the characteristic of oxides again later. Last is halogens. So halogens, they form various oxides, but then not all of them are actually pretty stable. Fluorine, OF2 and O2F2. OF2 is thermally stable at 298 Kelvin. Now, actually, we don't refer to fluorine, OF2 and O2F2 as oxides, but they're actually fluorides. And the reason we call them fluorides is because fluorine is more electronegative than oxygen. And these are actually very good fluorinating agents. So O2F2 oxidizes plutonium to PuF6. So this actually has the real life application of removal of plutonium from the used up nuclear fluid. Next, chlorine, bromine, and iodine. So as we know, their oxidation states can range from +1 to +7. Remember. So because of that, they are able to, they form various oxides, and stability of them is iodine is more stable than chlorine, which is more stable than bromine. And this is based on certain kinetic and thermodynamic factors. So in case of iodine, because first of all, the bond polarizability is high between the oxygen and the iodine atom. And because of that, these are insoluble solids and they decompose on heating only. So they're quite stable. I2O5 is actually a good oxidizing agent. Next, chlorine. Multiple bonds can be formed between chlorine and oxygen, and this is because of the availability of the d orbital. So this means that there is a lot of stability. So chlorine oxides, you have so many Cl2O, ClO2, Cl2O6, Cl2O7, and they're very good oxidizing agents, but they have a tendency to explode. Now, chlorine, ClO2, is actually used as a bleaching agent. Last is bromine. Now here, in this case, you had a greater polarizability. Here you had the availability of d orbitals. Bromine has neither of these two. And because of that, the stability of oxides in case of bromine is the least. It can form Br2O, BrO2, and BrO3 oxides. But these are powerful oxidizing agents. Next is reactivity towards halogens. Now these elements, they form EX3 and EX5, where X can be any halogen atom. Now nitrogen does not form a pentahalide, so it will not form NF5. No, but the thing is, the pentahalides are actually more covalent than trihalides, and the reason for this is because of the more polarizing power. So the bond is more polarized in case of +5 oxidation state than +3. And because of that, +5 is more covalent than +3, or rather pentahalides are more covalent than trihalides. So all the elements, trihalides, except for I am so sorry, excuse me. So trihalides in these elements, except for that of nitrogen, are actually stable. So any other trihalide are stable. But in case of nitrogen, only NF3 is found to be stable. Now, BiF3 alone is not covalent. The remaining trihalides are all covalent in nature. Next, you have the oxygen family. You have EX6, they can form EX6, EX4, as well as EX2. Now, stability is obviously fluorine is having the highest and iodine the least, and this is obviously because of the size of the respective ions. Now, in case of hexahalides, the hexafluorides alone are more stable because it is a small sized ion, and because of that, it's quite stable, and it has an octahedral structure. Next, SF6 is actually very stable for steric reasons. So oxygen can't form a hexafluoride, okay, because of the inability or unavailability of d orbitals. Sulphur, on the other hand, can. And because of this steric, there'll not be a lot of steric hindrances in case of SF6, and because of that, it is stable. Now, SF4 is a gas, SEF4 is a liquid, and this is tetrahalides. So they have 4 halogen atoms. So SF4 is a gas, SEF4 is a liquid, TeF4 is a solid. So they have an sp3 hybridization. So they are sp3 hybridized, and the shape is going to be trigonal bipyramidal. In this case, it's in hexa, it's octahedral, and in case of tetrahalides, they are trigonal bipyramidal. Next is dihalides. Except for oxygen, they form all of these elements. They can form dichlorides as well as dibromides. Now, in this case, the dihalides, the hybridization is sp3, and the shape is going to be tetrahedral. And monohalides, they're dimeric, which means they consist of 2 simpler molecules, and they can undergo disproportionation. As I told you, disproportionation is the parallel simultaneous oxidation as well as reduction. So these monohalides can undergo disproportionation reaction. Next, halogens, they form with themselves to form interhalogen compounds. And when we discuss, you have that in detail after we learn about the various compounds of halogens. So it forms X dash, where X is a larger sized halogen, whereas X dash is a smaller sized halogen. The last is the reactivity with metals. So reactivity with metals, we're not talking about for group 16, we'll be talking about 15 and 17. Because all of these metal elements in the group 15 will react with metals, and they're going to be reacting it at a -3 oxidation state. Basically, they pull 3 electrons towards themselves. So here you have a list of various compounds like calcium nitride, calcium phosphate, sodium arsenide, zinc antimonide, and magnesium bismuthide as various examples. The last one, halogens on reaction with metals, they form metal halides. So here you have magnesium reacting with bromine to form MgBr2. And as we go down the group, the ionic character is decreasing. And M over here is any monovalent metal. So if suppose, generally metals don't just show one oxidation state, there's a chance that might show more than one oxidation state. So the halides in the higher oxidation state will be more covalent than the ones in the lower oxidation state. So the halides at the high oxidation state will be more covalent than the one in the low oxidation state. With that, we're done with the chemical properties. So let's start with the chemical properties of noble gases. These elements have the least ability to react because of their most stable electronic configuration of Ns2 Np6. So because of that, they have a high ionization enthalpy, and they also have a positive electron gain enthalpy. Now, scientists, after the discovery of noble gases, wanted to synthesize various compounds, but it was actually quite difficult, again, because of these conditions. So it was only in March 1962 that a scientist, Neil Bartlett, was able to observe a particular reaction with noble gases. He actually started with the preparation of O2 plus PTF6 minus compound. And he noticed that the ionization enthalpy of molecular oxygen, notice we use the word molecular, we are not talking about the atomic, we're talking about molecular oxygen, was actually similar to that of xenon. And that's when he tried to synthesize a similar compound, and he landed up synthesizing this one, that is XePTF6 minus. And this was done by mixing two things, that is PTF6 and xenon. Now, from there, xenon compounds have been synthesized where xenon reacts with a very highly electronegative element like fluorine and oxygen. Now, krypton, on the other hand, they're lesser. It's only a krypton difluoride that has been synthesized and studied in detail. But compounds of radon, they've not even been isolated, but they've been identified. In case of argon, argon, neon, and helium, they're not even known as of now. Because these elements are relatively all the more stable than these ones. As we go down the group, the atomic radius increases. So let's start with these xenon fluoride compounds. So xenon fluoride compounds, you have binary fluorides so the preparation is done by direct reaction of the elements under basic conditions, specific conditions. So these are the preparation reactions. If you notice here, in case of xenon difluoride, you have xenon in excess. In case of xenon tetrafluoride, you have it in 1:4 ratio of xenon to fluorine. And in case of xenon F6, that is hexafluoride, you have 1:20 ratio, which means fluorine is way more higher. There's another preparation method for xenon hexafluoride, that is the reaction of xenon tetrafluoride with O2F2. And this is at 143 Kelvin. Now, physical properties, all of these are colorless crystalline solids in the sublime at 298 Kelvin. First of all these fluorides, they are good fluorinating agents, and they get hydrolyzed. Even in a little bit of water, they undergo hydrolysis. And the hydrolysis gives us xenon and hydrogen fluoride, as well as oxygen. Now, when these compounds react with fluoride ion acceptors, they act as cationic species, whereas with fluoride ion donors, they form fluoroanions. So those are the reactions given over here. Now, their structures, our xenon difluoride is a linear structure. In case of xenon tetrafluoride, you have a square planar. And in case of hexafluoride, you have an distorted octahedral structure. And this is because you have 6 bonding pairs and 1 lone pair of electrons. So because of that, it has a distorted shape, distorted octahedral shape. Next, xenon oxygen compounds. The hydrolysis of XeF4 and XeF6 with water gives us XeO3. That is hydrolysis of xenon tetrafluoride and hexafluoride. Both of them give us XeO3 trioxide. So partial hydrolysis actually gives us some compounds called as oxyfluorides. So oxyfluorides, basically they have both oxygen as well as fluorine, and the reactions are here. Xenon trioxide has a colorless and it's an explosive solid. The shape is pyramidal, whereas XeOF4 is a colorless volatile liquid. So it is both of them are colorless. If you notice, all of these compounds are colorless in nature. XeO3 is so solid, and all the xenon fluorides are solids, whereas XeOF4 is a volatile liquid. And the shapes for this one is pyramidal in XeO3, and in case of XeO4, OF4 is a square pyramidal structure. Now let's just jump to the uses. So you have the uses of helium, neon, and argon given in the notes, and just go through it. And with that, we're done with the chemical properties. At this point, I think we're done with the group 17 altogether. So the elements in the second period tend to show certain unique behavior due to their small size. So here we'll start with studying about the anomalous behavior of nitrogen, oxygen, and fluorine. So nitrogen differs from the other elements of its group because of its small size, high electronegativity, high ionization enthalpy, and the unavailability of d orbitals. Now, it has the ability of, this is unique, it has an ability to form p-pi multiple bonds with itself and with smaller elements like carbon or oxygen. But the other elements of this group don't have the tendency to form a p-pi bond. The reason for this is because of the no proper overlap between the orbitals. Now, nitrogen, as we know, can have it forms 3 bonds with itself, basically N triple bond N. And this is very stable. As we know, 78% of the atmosphere is made up of that. And because of that, we're able to exist on this planet. So the bond enthalpy is extremely high. Now, phosphorus, single bond, arsenic is also having a single bond between the atoms, antimony is also having a single bond, whereas bismuth actually forms a metallic bond. Nitrogen, but one important thing, nitrogen single bond is weaker. And because this is weaker, the catenation is lower in case of nitrogen. So this is weak in the first place is because of the repulsion between the non-bonding electrons. Next, the absence of d orbitals means that it cannot form a p-pi bond. Excuse me. So it cannot form with heavier metals, unlike R3p double bond O, where R is excuse me, alkyl group. I am so sorry. So covalency, as we know, for nitrogen is only 4. It can't form more bonds than 4 when it forms a covalent bond. On the other hand, phosphorus, arsenic can actually form d-pi, p-pi bond, even with transition elements. So basically, when to just summarize, you have p-pi bond, multiple bond nitrogen can form with itself, and it cannot form, this p-pi bond cannot be formed by the other elements. They can only form p-pi d-pi bond. Nitrogen, on the other hand, can't form the p-pi d-pi bond because of the unavailability of the orbitals. The nitrogen diatomic molecule is quite stable, and yeah, that's about it. Next, anomalous behavior of oxygen. Obviously, it's again going to be due to small size and high electronegativity. It's the same in both cases, if you notice. So this is again implied in strong hydrogen bonding in H2O, but H2S does not have a strong hydrogen bonding. So because of its absence of d orbitals, it does not have, its covalency is going to be just 4, but it does not even exceed 2. It's very rare actually. Next, in case of fluorine, it's because of the small size, high electronegativity, low FF bond dissociation enthalpy, and the unavailability of the orbitals in valence shell. Notice it's almost similar, all of these, so don't spend time, you know, studying it separately, these three, that is. So the ionization enthalpy, electronegativity, and the electrode potential are higher for fluorine than expected for compared to the other elements of its group, it's higher. And in case of ionic and covalent radii, melting point, boiling point, enthalpy of bond dissociation, electron gain enthalpy are actually lower than what we expect it to be. And this is because of small and strong bond formed by fluorine. I'm sorry, this is due to the small size and all these, because of all of these are the properties which are observed. Now, because of its small size and strong bond formed, most of the reactions done by fluorine are actually exothermic in nature. So it actually forms only one oxo acid. We'll be learning about the various oxo acids formed by halogens. And HF is actually a liquid and its boiling point is 293 Kelvin. Because of its hydrogen bonding character, um, hydrogen bonding exists in the first place because fluorine is highly electronegative in nature and it's very small in size. So other hydrogen halides, they have a bigger size and electronegativity. They're actually gases. So only a halogen, that is halogen acid, that is HF, is a gas, is a liquid. The remaining are actually gases. So that we're done with the anomalous behavior of nitrogen, oxygen, and fluorine. Compounds of nitrogen. So nitrogen, we'll be learning about three main ones, that is dinitrogen, ammonia, as well as nitric acid. Let's start with dinitrogen. Dinitrogen, the commercial production is by liquefaction as well as the fractional distillation of air. And this gives us dinitrogen in the end. Laboratory preparation, you have the ammonium chloride reacting with sodium nitrite to give us dinitrogen, water, and sodium chloride. And nitrogen oxide and nitric acid are also formed over here, and they are basically removed by passing the particular gas through sulfuric acid, and which has potassium dichromate. The next one is thermal decomposition of ammonium dichromate, which gives us dinitrogen and water, as well as chromium 3 oxide. The reaction is given over here. Next, the thermal decomposition of sodium or barium azide gives us pure nitrogen. So the barium azide is undergoing decomposition to give us barium as well as dinitrogen. Ammonia, the preparation, the first one is, as we know, there are various organic compounds which consist of nitrogen. One of them is urea. When it undergoes decay, first it's forming ammonium carbonate, which on further decay is forming ammonia, water, and carbon dioxide. The second method of preparation is from ammonium salts. So ammonium chloride and ammonium sulfate here, both of them are reacting with calcium hydroxide as well as sodium hydroxide respectively to lead to the formation of ammonia and water. Notice there are two compounds which are, the products are the same, that is ammonia and water. And here in this case it's calcium chloride, and in this case it's sodium sulfate. So this calcium is combining with this chlorine, calcium chloride, sodium sulfate combining with this SO4. Last is the Haber's process. Haber's process is actually used for the manufacture of ammonia on a large scale. So what happens is nitrogen is reacting with hydrogen to form ammonia. It's at 773 Kelvin, and this particular thing, the Le Chatelier's principle, shows that when there is an increase in pressure or a high pressure, will make sure that the reaction moves in the forward direction. So the pressure is going to be at 200 into 10 to the power 5 pascals, and temperature is at 700 Kelvin. It's approximately 700 Kelvin. So the catalyst used over here is K2O and Al2O3. And previously, actually, it was iron which was used as a catalyst, but and molybdenum as a promoter. So the diagram is actually given in the textbook for you to just look at it. Nitric acid, nitrogen forms various oxo acids. Nitric acid is the most important one. Laboratory preparation is done by heating sodium nitrate or potassium nitrate with sulfuric acid to give us sodium hydrogen sulfate and nitric acid. Large scale preparation is done by something called as Ostwald process. So Ostwald process consists of 3 steps. First step is the oxidation of ammonia in the presence of platinum rhodium gauge catalyst to give us nitric oxide. This nitric oxide is further combining with oxygen to give us nitrogen dioxide. Nitrogen dioxide is going to dissolve in water to give us nitric acid. So generally, the nitrogen monoxide, which is formed as a byproduct, is recycled. And this gives us a concentration of 68% by mass of nitric acid. But this can be increased by dehydrating nitric acid with sulfuric acid, concentrated sulfuric acid. Next, let's talk about physical properties. First of all, with dinitrogen, it is a colorless, odorless, tasteless, non-toxic gas. And nitrogen actually exists in 2 stable isotopes, that is 14 nitrogen and 15. And it's low soluble, not that soluble in water, and it has a low freezing as well as boiling point. Ammonia, on the other hand, is a colorless gas with a very pungent odor. It stinks, basically. I've had to sniff ammonia in the lab, and it's not a very pleasant experience, if I'm being very honest. So freezing point and boiling point is 198.4 Kelvin and 239.7 Kelvin, respectively. In solid and liquid state, ammonia actually shows hydrogen bonding. And because of the presence of hydrogen bonding, ammonia has a higher melting as well as boiling point. The shape is a trigonal pyramidal shape. And here, if you see, there's a lone pair of electrons at the top, and it has 3 bond pairs, which give the trigonal pyramidal shape. Nitric acid, on the other hand, is a colorless liquid. Notice these two are gases, whereas this alone is a liquid. Its freezing point is 231.4 Kelvin, and boiling point is 355.6 Kelvin. So as I told you, generally when we use it in the lab, it has approximately 68% of nitric acid, and its specific gravity is 1.54. In gaseous state, nitric acid is actually planar in nature. That is, it has a planar shape. So while studying these, don't study them individually. Instead, just do them as a parallel. If you do it parallelly, you'd be able to easily remember various things. Next is chemical properties. Let's start with dinitrogen. Dinitrogen is obviously very inert at room temperature. This is because of a high bond and dissociation enthalpy of nitrogen. Now, when we react with metals at high temperatures, it combines with metals, whereas to form ionic hydrides, nitrides. I'm sorry, this is supposed to be nitrides. Whereas in case of non-metals, they form covalent nitrides. So here you have a reaction with lithium as well as magnesium to form the respective nitrides. Haber's process is basically, as we learned, the synthesis of ammonia. So that's done using dinitrogen. Combination with dioxygen. So when it combines with dioxygen, it gives us nitric oxide. Notice that was one of the products over here. Yeah. And in the Ostwald's process. The next is ammonia. Ammonia is actually basic, and it's basic due to the formation of the OH minus ions, but it's a very weak base because of its formation of the OH minus ions. It acts as a Lewis base because of the lone pair of electrons on the nitrogen. And this in turn forms complex compounds which are helpful for detection of certain metals like copper and silver. So it actually leads to the formation of various complexes when it reacts with copper and silver. And that is actually used for the identification of these specific metals. Next is formation of ammonium salts. So when ammonia reacts with acids, they form ammonium salts. So it basically helps in the precipitation of hydroxides because it is weakly basic. And here you see, if you have zinc sulfate reacts with ammonium hydroxide to give us zinc hydroxide, which is a white precipitate when ammonium sulfate. So it is able to form, these salts are able to undergo various reactions. Next is nitric acid. Nitric acid, obviously, as the name suggests, it's a strong acid. It's an acidic substance. So When it reacts with metal, it actually acts as a very strong oxidizing agent, but it does not react with all the metals. It only reacts with certain ones. I mean, basically, it does not react with noble metals like silver, gold and platinum. And the product which is formed during this particular reaction is dependent on three things: the concentration, the temperature, and the nature of the material undergoing oxidation. So in case of copper, if it reacts under a dilute condition, you have the formation of nitric oxide. If you see, the main product with copper is the same in both cases, but the byproducts are different. So here you have nitric oxide, here you have nitrogen dioxide. Again, here with zinc, in dilute oxide, you get nitrogen oxide, that is N2O. And in case of concentrated nitric acid, you get NO2, that is nitrogen dioxide. So remember the conditions, based on conditions of the acid, you have variation in terms of what are the byproducts formed. And obviously based on the material, you have the byproducts also varying. Now, many materials like chromium and aluminium. Aluminium, if you notice, you have an aluminium oxide forming on its surface. So because of that, these don't dissolve in concentrated nitric acid. Now, the next is reaction with non-metals. So it has an ability to oxidize non-metals. So iodine is converted to iodic acid, carbon is converted to carbon dioxide, sulfur to sulfuric acid, phosphorus to phosphoric acid. And the respective reactions are given over here. If you notice, the byproduct is NO2 in all the cases and H2O. The main product is varying. So do not, learn these individually, learn them as a whole bunch. And basically the byproducts are the same in all the four cases. It's only the main product, that is the acids which are formed, which are different. Next is the Brown ring test. Brown ring test is actually used for the detection of nitrates. So what happens is, we take a test tube and we have we add ferrous sulfate solution to it, and then concentrated sulfuric acid is added along the sides of the test tube. So what happens is, a brown ring is formed at the intersection between these two, and this shows the presence of nitrate ion. And this is because Fe+2 can reduce nitrate to nitric oxide. And this in turn leads to the formation of an Fe+2 to form a brown colored complex. And that is what is observed in the brown ring test. Here at the bottom, you have the various uses of nitrogen, dinitrogen, ammonia, as well as nitric oxide. Just go through them. There are various oxides of nitrogen which you observe. So here in this table, you have a compilation of the oxidation state, the formula, the name, the common methods of preparation, their appearance, resonance structures, and bond parameters. Do go through all of these. And it's since in your textbook, it's in two different tables. I instead compiled it into just one, so you don't have to, basically, you can learn it all in one go. With that, we're done with the various compounds of nitrogen. I know I told that I tried to finish it by 1 hour, but I think I have exceeded my time. So let's start with compounds of oxygen. So first you have dioxygen. Dioxygen methods of preparation, you have 3 of them. First is by basically heating the salts which contain oxygen. Second is by thermal decomposition of metal oxide. So we have various metal oxides. When they are heated, they form the oxygen molecule, whereas the hydrogen peroxide actually decomposes to give dioxygen and water. And the catalyst over here in this reaction is a finely divided metal and manganese dioxide. The large scale preparation is basically the electrolysis of water, and this is done. And when this is done, you have the release of hydrogen in the cathode and release of oxygen at the anode. Whereas for the industrial preparation, they obtain it from the air itself. So carbon dioxide and the water vapor is removed. The rest of the gases are liquefied. If you remember, one of the methods to prepare dinitrogen was this one. So dioxygen is colorless, odorless, and it's soluble in water. And this solubility in water has made sure that there is life even in oceans and seas, that is marine or aquatic life. So it liquefies at 90 Kelvin and it freezes at 55 Kelvin. So oxygen's isotopes are 16 oxygen, 17 and 18, whereas O2 is paramagnetic in nature. So let's just look over the various chemical properties. First is reactions with metals and non-metals. So oxygen, due to its high electronegativity, has a tendency to react with almost all the elements in the periodic table. It does not react with gold and platinum because they are noble metals. And when it reacts with other elements, it actually is a very strong exothermic reaction. Fun fact, rusting of iron in itself is actually an exothermic reaction. If it had happened in a moment, if it was basically taking place in a moment, it would have been extremely exothermic and the amount of energy released would be very high. The only reason you don't feel the heat is because of the fact that it's a very slow process. So, but in some cases you have, it requires some amount of energy. Here you have various reactions of oxygen, dioxygen reacting with elements like calcium, aluminium, phosphorus, and carbon, zinc, and methane. So these are the various reactions, and oxygen, dioxygen reacts with metals, non-metals, and in this case, it's even a compound. Even compounds are reacting with it. Next is catalytic oxidation of compounds. So various compounds like sulfur dioxide, HCl undergo oxidation with using dioxygen in the presence of a catalyst. Here in sulfur dioxide, it's V2O5, vanadium pentoxide, and in case of HCl, it's actually CuCl2. So this leads to the formation of the respective products. The uses, these are just basic, you can just go through them, they're theoretical topics. Next is ozone. Ozone is actually an allotropic form of oxygen. It has O3 is the formula, right? And the ozone layer, as we all know, at this point, everybody is familiar with that. So it protects us from the UV rays of the sun. So the preparation is done through a process where we take a dry stream of oxygen through a silent discharge, and this leads to the conversion of the oxygen to the ozone, and this is called as ozonized oxygen. And this is an endothermic process, which means it requires some amount of energy, and the silent electric discharge is actually also used for the prevention of decomposition of the ozone. So if 10% higher concentration is required, battery of ozonizers can be used. Physical properties. It is a pale blue gas, a dark blue liquid, and a violet black solid. So in the respective conditions, if it's a gas, it's a pale blue colored. If it's liquid, it's dark blue. And if it's solid, it's actually a violet black. It has a very characteristic odor. At small concentrations, it's quite harmless. If you happen to get up very early in the morning, you have this fresh smelling air. That's because of the presence of nascent oxygen, and that's actually because of the breaking of oxygen atoms, ozone molecules to give us the nascent oxygens. Completely off topic, but yeah. So that's the characteristic odor for the nascent oxygen. Even ozone has a characteristic odor. At small concentrations, actually quite harmless, but at higher concentrations, that is 100 parts per million, it's very uncomfortable and causes headache, nausea, etc. So basically the O3, that is ozone, it undergoes decomposition into oxygen. And this means that ozone is actually unstable. And there are two effects which make the negative Gibbs energy large for the conversion into oxygen. So high concentrations of ozone actually makes it explosive in nature. So there are two factors: thermodynamically unstable and large negative Gibbs energy change for conversion to oxygen. This in turn means that the ozone is actually at high concentrations, it's very explosive in nature. The oxygen-oxygen bond length is almost similar. So it's 128 picometers, and the bond angle is 117 degrees, and the shape is angular. So it exists as a resonance hybrid of these two forms rather. Now, oxidizing agent, since, as I told you, it liberates nascent oxygen, so it's a very good oxidizing agent. So lead sulfide gets converts to lead sulfate. Iodide ion gets converted to iodine. One more thing, estimation of ozone gas is done with using it reaction with the excess of potassium iodide solution. And this forms iodine. The iodine form is again titrated against a standard, and that will give us the quantity or the amount of ozone. Now, as we know, there was a lot of issues when previously when chlorofluorocarbons were used as a refrigerant, that led to a major issue of a hole in the ozone layer. So nitrogen monoxides, so there are various other threats to the ozone layer itself. So nitrogen monoxides can combine with ozone, and this leads to the formation of nitrogen dioxide and oxygen. And these are actually an exhaust from the airplanes, and they cause the breakage of the ozone molecule. There are other things called as pheromones, which are used in sprays and refrigerants, which are threats to the ozone layer. So these are the various uses of ozone. Let's move on to some oxides. So oxygen is one of the most reactive elements, and it forms various compounds with almost all the elements in the periodic table. So oxygen, these are called as oxides. Okay, so oxide is basically a compound which has an oxygen with another element. So it's classified into two, simple oxides and mixed oxides. So simple oxides, they will only have a metal or non-metal and oxygen. And the number of atoms of oxygen is equal to the valency of that particular element, that is metal or non-metal. Whereas mixed oxide, excuse me, is actually formed by the combination of simple oxides. And the simple oxides which do form this mixed oxide can be same or different. Next is classification based on its nature. This is specifically for simple oxides. You have three: acidic, basic, and amphoteric. Acidic oxide combined with water to form an acid. Basic oxide combined with water to form a base. Amphoteric act as both acid and base. So here you have sulfur dioxide reacting with water to give sulfuric acid. So generally, non-metals form acidic oxides. But there are some oxides which are of metals which do exist, and they form when their oxidation state is extremely high. Basic oxides, on the other hand, are formed by metals, and amphoteric are by some metals which act as both acidic as well as basic. So here, when aluminium oxide is reacting with an acid, it itself will act as a base. When aluminium oxide is acting with a base, it itself will act as an acid. Neutral oxides, on the other hand, are neither acidic nor basic. So water is a neutral oxide, nitrogen oxide, carbon monoxide, all of these are neutral oxides. With that, we're done with the various compounds of oxygen. For sulfur, we'll be talking about the allotropic forms of sulfur first. So it has various allotropes, but two of them are most important. That is rhombic sulfur, yellow rhombic sulfur, and monoclinic sulfur. So let's start. First of all, color of rhombic is yellow. For monoclinic, it's colorless. Melting point of rhombic is 385.8 Kelvin, and in case of monoclinic, it's 393 Kelvin. The specific gravity is 2.06 for rhombic and 1.98 for monoclinic. Preparation is done by evaporating a solution of rolled sulfur in carbon disulfide, and this will give rhombic crystals. Now, rhombic crystals are actually unstable, and they've at temperature above 369 Kelvin. So that is the basic idea used for the synthesis of monoclinic sulfur. So rhombic sulfur is heated in a dish or melted in a dish, and then it's cooled till the crust is formed. The liquid which is present below that is removed by drilling two holes or making two holes. And at the bottom, you'll see that the crystals, the needle-shaped crystals of beta sulfur or monoclinic sulfur is formed. So rhombic sulfur is insoluble in water, and it is to an extent soluble in benzene and carbon disulfide, whereas monoclinic is soluble in carbon disulfide. So alpha sulfur, it's stable below 369 Kelvin, and it converts to beta sulfur. So above 369, it will get converted to beta sulfur. So obviously the stability is the opposite. Above 369, monoclinic is stable. Below that, it will convert to rhombic sulfur or alpha sulfur. So the 369 Kelvin is actually referred to as transition temperature. So at this temperature, both the structures are stable. So both rhombic as well as monoclinic structures will be stable at 369 Kelvin. So here you have the two structures of S8, ring in rhombic, and S6 form as well. So various modifications have 6 to 20 atoms. So S6 actually adopts a chair form, so it's a chair shape. And S2 is present at elevated temperatures, that is about 1000, approximately 1000 Kelvin. And it is a dominated species and it's paramagnetic, similar to that of oxygen. So let's start with sulfur dioxide. So sulfur dioxide, the preparation method is done when sulfur is burnt in air. So sulfur in presence of air gives rise to sulfur dioxide. The next one is the laboratory preparation. You have sulfite. It's getting treated in the presence of dilute sulfuric acid. That's 2H plus and implies that the dilute sulfuric acid gave up the H plus ions, and this leads to the formation of sulfur dioxide. Third is the industrial preparation. So roasting of sulfide ores, one of the byproducts formed is sulfur dioxide. So that gas is dried and liquefied under pressure, and that's stored in steel cylinders. So sulfur dioxide is a colorless gas. It has a pungent smell. It's highly soluble in water, and it liquefies at room temperature and pressure of 2 atmospheres. Now its boiling point is 263 Kelvin, and this is the molecular structure of sulfur dioxide. So it exists as two resonance hybrids or two resonance structures. So when sulfur dioxide is passed through water, it leads to the formation of something called as a sulfurous acid. That is H2SO3, not sulfuric acid, sulfurous acid. So when it reacts with sodium hydroxide, it forms sodium sulfide. This is then treated with more sulfur dioxide to form hydrogen sulfide. Sodium hydrogen sulfide. First, you're getting sodium. First, you get sodium sulfide, and that is further reacting to give us sodium hydrogen sulfide. Now, it reacts with both water as well as alkalis, and it behaves similar to that of carbon dioxide. Now, reaction with chlorine leads to the formation of sulfuryl chloride, that is SO2Cl2. Sulfur dioxide undergoes oxidation or is oxidized in the presence of vanadium catalyst, and it leads to the formation of SO3, that is sulfur trioxide, and it acts as a good reducing agent because it helps in the conversion of iron 3 ions to iron 2 ions, and it also decolorizes the acidified potassium permanganate. And in this particular reaction, the decolorization of acidified potassium permanganate is used for the identification of the presence of sulfur dioxide. Here you have the various uses of sulfur dioxide. Let's move on to the oxo acids of sulfur. So as I told you, oxo acid is any acid that contains oxygen. And so the oxo acids of sulfur are given as below in the table. Here you have, it has only one sulfur atom, two sulfur atoms, here two or more. So this actually is given as one single line, and I thought maybe if it's in a table, it'll probably be easier for you to remember. So some of them are basically can't be isolated. So they are known in the aqueous solution or in the form of their salts. So here you have sulfurous acid, sulfuric acid, peroxo disulfuric acid, and pyrosulfuric acid, that is oleum. Remember pyrosulfuric acid and sulfuric acid. So let's start with sulfuric acid. It's one of the most important industrial chemicals. First is the manufacture by contact process. So contact process actually consists of 3 steps. The first one is burning sulfur or sulfide ores, and this generates sulfur dioxide. So the sulfur dioxide is going to be impure. It has to be purified, and that's done by removing the dust and various impurities like arsenic compounds. The sulfur dioxide, see, this is the impure and it's getting purified by various methods. Now, the sulfur dioxide is converted to SO3 using a catalyst. So sulfur dioxide in the presence of oxygen is going to get converted in the presence of vanadium pentoxide to give us SO3. So this is actually an exothermic reaction, and this is reversible in nature. So because to make sure that the reaction is going to basically move in the forward direction, low temperature and a high pressure is used here. So this SO3 which is formed is going to get converted to um, basically it's going to get absorbed in concentrated H2SO4 to give oleum. And this oleum is diluted using water to give sulfuric acid of desired concentration. So usually in the industry, two of these steps are basically going to take place parallelly. And the sulfuric acid which is obtained is 96 to 98% pure. So there's going to be a spray of sulfuric acid. So SO3 is getting converted to oleum. This oleum is dissolved in water to give us sulfuric acid. So just once I'll go through it once more. You have sulfide ores. Burning of that is giving us sulfur dioxide, SO2. This SO2 is converted to SO3 by reaction with vanadium in the presence of vanadium pentoxide. And this SO3 is converted to oleum in the presence, using sulfuric acid. Now, the oleum is dissolved in water to give us sulfuric acid. The physical properties, colorless, dense, oily liquid. The specific gravity is 1.84 at 298 Kelvin. Freezing point 283 Kelvin, boiling point 611 Kelvin, and it dissolves in water with the evolution of large amount of heat. Honestly, once I made a mistake of adding water. So always in the lab, you have a confusion, water to acid, acid to water. It's always acid to water. Once I did the other way around and the test tube got too hot that it actually broke. So you have to be very careful while doing the same. So chemical properties of this, the reactivity is due to the four reasons. First is low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. In water, it ionizes in two steps. And the Ka value, the first step is extremely high. This implies that it's very easy for H2SO4 to dissociate to form these two ions. And because of that, it is a highly acidic substance. Next is formation of salts. Obviously, acid plus what base forms salt plus water. So in the presence of it forms two series of salts. So normal sulfates, that is sodium sulfate, copper sulfate, etc. And in presence of acid, it also forms acid sulfate like sodium hydrogen sulfate. Next, it forms salts from various acids as well. So it is basically used to manufacture salts of more volatile acids. Dehydrating agent, it is a very strong dehydrating agent. When you add H2SO4 to carbohydrate or like any organic compound, basically it dehydrates it and you get a black charged substance. So sulfuric acid is actually used as a drying agent, and various substances are passed through sulfuric acid to give, as long as the sulfuric acid does not react with that substance, they're actually used as a dehydrating agent. It is acts as an oxidizing agent as well. So hot concentrated sulfuric acid is moderately oxidizing. So metals and non-metals are oxidized by concentrated sulfuric acid, which is going to get reduced to sulfur dioxide. So here, if you see, copper is undergoing oxidation to form copper sulfate, sulfur to sulfur dioxide, and carbon to carbon dioxide. So these are the various uses of sulfuric acid. It has a diverse uses. One of the uses in battery acid as well. So with that, we're done with the various compounds as well as the allotropes of sulfur. This is the last topic, I swear, compounds of halogens. So first we'll be learning about chlorine, hydrogen chloride, and then we'll be talking a little bit about the oxoacids of halogens as well as the interhalogen compounds. Let's quickly start with chlorine. Chlorine was actually discovered in the year 1774 by the action of HCl on MnO2 by Scheele in Scheele. So it was Davy who basically, studied its nature and gave the name chlorine, because chloros meant greenish yellow. So the preparation is first one is by heating manganese dioxide with concentrated hydrochloric acid. So when this happens, you have magnesium chloride with chlorine and water. Sometimes instead of just using concentrated hydrochloric acid, we use a mixture of sodium chloride and concentrated sulfuric acid to give us the same compound. So notice you have a difference here. You have NaHSO4 as one of the byproducts being formed. Next is by using potassium permanganate. Potassium permanganate is going to really react with uh, hydrochloric acid. And if you notice, there is to an extent some amount of similarities between the various byproducts and the products formed. Next, the manufacture of chlorine is done using something called as Deacon's process. So hydrochloric acid is undergoing oxidation in the presence of copper chloride as a catalyst to give us chlorine gas. The electrolytic process that is of concentrated sodium chloride solution, that is brine, will give us chlorine at the anode. And one more thing, it's obtained as a byproduct in various industries. The properties of chlorine are, it's a greenish yellow gas. It has a very pungent and it has a very suffocating odor, and it's heavier than air. It liquefies very easily and boils at 239 Kelvin, and it's soluble in water. So chlorine reacts with various metals and non-metals. So when it reacts with these metals and non-metals, it leads to the formation of chlorides, and that is based on their oxidation state. By crisscross method, you can figure out the formulae of the chlorides. Next is the reaction with hydrogen containing compounds. So it reacts with them to form HCl. So the main product is going to be HCl in all the three cases, but the byproducts are going to be varied with respect to the substance it reacted with rather. Reaction with alkalis, with cold and dilute alkalis, it produces a mixture of chlorides and hypochlorites. Here you have NaCl and NaOCl. And hot, it forms a mixture of chloride and chlorate. So based on the condition that it undergoes the reaction at, it leads to the formation of various products. On reaction with slaked lime, it forms bleaching powder, and bleaching powder has variety of uses. With hydrocarbon, it leads to the formation of saturated hydrocarbons. And in case of substituted, you have a saturated hydrocarbon, and with addition reaction with unsaturated hydrocarbons. Basically, in saturated hydrocarbons, if you remember, it's just undergoing substitution. Whereas in case of unsaturated hydrocarbons, this double bond will break to give us, again, addition product. With water, it loses its color and forms HCl and HOCl. So the HOCl is actually the reason why we have the bleaching properties of chlorine existing in the first place. So chlorine also oxidizes, that is a good oxidizing agent. It oxidizes ferrous to ferric, sulfite to sulfate, sulfur dioxide to sulfur trioxide, and iodine to iodate. So the reactions are given over here. All of them in the presence of the reacting with Cl2 to give us variety of products. Bleaching agent, chlorine is a powerful bleaching agent because of its due to oxidation. So as I told you, it forms two products, HOCl and HCl. The nascent oxygen from HOCl gives its bleaching agent. So the effect of its bleaching power is actually permanent, and these are the various uses of chlorine. Next, we'll go and look into hydrogen chloride. So it was prepared first by Glauber in the year 1648. What he did was he heated common salt with sulfuric acid. So he heated sodium chloride with sulfuric acid. Remember, that's exactly what we did here as well. So the lab preparation, sodium chloride on heating with sulfuric acid gives us the hydrochloric acid. So the HCl which is formed over here is dried using the concentrated sulfuric acid, because concentrated sulfuric acid can be used as a good drying agent. So the physical properties are, it's colorless, has a pungent smell, and it's easily liquefied to colorless liquid, and it can be frozen to a white crystalline solid. Its freezing point is 159 Kelvin and a boiling point 189 Kelvin. It's soluble in water and it ionizes, and its Ka value dissociation is very high. So because its dissociation constant is high, it is very acidic in nature. On reaction with ammonia, it gives ammonium chloride. Aqua regia is very important. So basically, it consists of 3 parts of concentrated sulfuric acid, concentrated hydrochloric acid, and 1 part of concentrated nitric acid. And this combination can dissolve noble metals like gold and platinum. And the reactions due to which they undergo dissolution is given below. Decomposition of salts of weaker acids. So weaker acids like carbonates, hydrogen carbonates, and sulfides, etc., undergo decomposition in the presence of hydrochloric acid. So here, if you see, you have sodium carbonate, sodium hydrogen carbonate, or bicarbonate, and sodium sulfide. So these 3 are undergoing decomposition to give us carbon dioxide, sulfur dioxide, water in all the 3 cases, and sodium chloride in all the 3 cases. So just remember the respective products formed. So these are the various uses of hydrogen chloride. Next is the oxo acids of halogens. So fluorine can only form 1 oxo acid because of its small size. Remaining it does not form the other oxo acids, and the oxo acids cannot be isolated in pure state, so they are obviously isolated in the aqueous medium or their salts. So here in this table you have the oxo acid, the general formula. Do not sit and by heart all of these. If you just learn this, and if you learn which of these are formed, like chlorous acid alone is not formed by all of them, it's only formed by chlorine. Remaining all of the acids formed by all the elements. Leave out fluorine from the list. So, excuse me. All I'm trying to say is, do not learn each of these separately. Just learn this. Learn which of them are formed by which of the elements itself. So the next one is here the structures are given for the various oxo acids of chlorine. Next is the interhalogen compounds. So interhalogen compounds are formed when 2 halogen atoms are react with each other. So X and X dash. X is the halogen which has a larger size. X dash is the halogen of smaller size. And obviously, since X is bigger than X dash, it is more electropositive. Or X dash is more electronegative than X. So when the ratio between the radii of these increases, the number of atoms per molecule will also increase. So iodine and fluorine, which form an interhalogen compound, is IF7. They have the maximum difference in radii, and so that's because of the ratio of radii in between them is very high. So the preparation is by direct combination or by action of halogen on lower interhalogen compounds. So based on the various conditions, you have the formation of various products. So for example, over here, bromine and fluorine, when you have it diluted with water, you just have bromine trifluoride. When it is in excess of fluorine, you have bromine pentafluoride. So based on the conditions which are put forward and the quantities of the respective halogen atoms, you have variation in terms of kind of atom or kind of molecule which is formed. So here you have the various interhalogen compounds. Generally, these compounds are covalent. They are diamagnetic and they are volatile solids or liquids, except for CLF, which is gas. The physical properties, they are intermediate between the two constituents. So the chlorine and fluorine. So intermediate between these two will be the physical property of the particular interhalogen form. And melting and boiling point is actually a little higher than what is expected. So the chemical reactions which are shown by these interhalogen compounds are similar to that of the individual halogens. So generally, it's noticed that the interhalogen compounds have more reactivity than the respective halogens. And this is because the high reactivity is because the bond between halogens is actually stronger than the interhalogen due to variation in terms of size. And due to that, you have the X dash bond is actually weaker than the XX bond. And this, however, is excluding fluorine. As I told you, fluorine bond is actually quite weak due to the presence of repulsions. So they undergo hydrolysis and they give us the halide ion from the smaller halogen. So based on the based on the type of interhalogen compound, we have the anion derived with respect to the larger halogen. Okay, and based on the type of interhalogen, you have a hypohalite when it's XX dash, halite when it's XX dash 3, halate when it's 5 times, perhalate when it's X5, sorry, X7 dash. And the molecular structure of these interhalogens can actually be told with respect to the Vesper theory. So the Vesper theory here, you have bromine trifluoride. Now, bromine has 7 electrons in the valence shell. 3 of them are being used for bonding, and you have 4 more left as lone pairs. So they have 2 lone pair of electrons. So what happens is these bond pairs, they occupy corners, and the lone pair will occupy the equatorial positions. And this is to make sure that there is the least amount of repulsion between the lone pair, and bond pair, bond pair. So this is a bent T shape. Remember, this is the structure of bromine trifluoride. This is actually given as an example or question in your textbook. So with that, we're done with the chapter. I know I was supposed to finish the video under an hour, but we started on with learning about the general introduction, where we talked about the electronic configuration, the occurrence, the elements that belong to this group. Then we went on to talk about the physical properties and the various physical properties as well, and the chemical properties and the various compounds in each of these groups. So with that, we're done with the P block elements. If you found it helpful, do comment and do let me know if there's something that I missed out. And the notes are given in the description below, so do check it out.